Okay, we are back. Now it is customary to put after this line a check whether the action is completed or not. Let's have here an example. Let's say we are writing and maybe we will be reading also what we have written. And we think that we have assigned to my input a string. And let's assume this device, this entity that I have put over here is full. You meet this sometimes in our department as well. You have a quota for your file system and it is full. You have downloaded a film or whatever it is and you don't have a place to create a single file more. How will the operating system tell you about this? It will return a null pointer. So, returning a null pointer is the way fopen telling you I couldn't satisfy your demand. Therefore, we have a test for this. Either you do it like this, my input is equal to null to be more readable, or simply, since this plays the role of falsity, I put over here the exclamation mark, the negation mark. The negation of null must be true, one actually, and some error processing. Here goes in some error processing. I don't go into details what this can be. You can stop the program, you can give a warning to the user. You can go silently and open the file somewhere else. There are hundreds of, not hundreds, but tons of alternatives for this. So you do whatever you like in here. And if you are here, that means the fopen succeeded and you have a zero from scratch created, not a single byte existing file, which you have named as this one. Okay then. Now, then what will I do? If it is a textual file, then presumably I will write something or read something. The way to write to a file is print yes, no mistake over here. In contrary to the printf, this time you have here in the first argument of printf the file handle. So my input goes in here, and then all the formatting strings, etc. goes in here. Leave one space, an F, and let's say here I, and then some variable, grade. This part is exactly what you know from printf. The same would exist if you want to read something as scanf. For the moment, I know I opened the file with write, I'm writing. I have not explained how I go back. For that, you have to go into the topics of random accessibility, which will come later. But let's say I opened it with R, then that means there was some pre-stored data in there, and now I scanf it, because the moment I open a file with R, it starts from the top, from the 0 byte of the file to provide me the data. And it is exactly the same way I do printing to it. My input, and then comes the reading format and the variables, ampersand, the pointers to the variables which will receive the data. Here is nothing interesting actually. All is something that you know already from printf and scanf. Now, having said this, we have to, it is exactly the point to explain, to read big amounts of data. By the way, there are two other functions, read and write. I will not go into the details. Go and read it from the book. Read and write serves the purpose of reading big amounts of binary data into a place in the memory. Right? For example, if you open up an image file, you will read it in with read or write it with write. Right? It is the way you dump down an array full of information down to the disk or whatever it is, it could be any device, any string, and upload it from there into an array. Go and read it. I will not go into those details. It is boring and very understandable from the book. What I want to consider is something else, something related to efficiency. Now, let's assume you are writing a code which reads in some huge newspaper text or book text, right? Book is better. You have a text file which holds 500 pages of some text. And your job is to make some statistics on the text. Let's say you will be searching how many adjectives is used in the text. You are doing some NLP study or analysis, or you are looking for some keywords to find out what the book is about, what the text is about. I can find hundreds of reasons why you would do this. Okay. The key is this. You grab the text character by character. Presumably something like this, as will follow. Scanf, blah blah blah. Just one character, please. Or just one string from there. Percentage S into some buffer. Right? Or text buffer. Text. Yes. Nice. What will it read? It will read a single word till the first terminator, for example, a blank white space. Then you have this in a loop. You put this in a loop. While file is not at the end. Test for file not being at its end. Some test, right? And you read it, then you process the word. And here goes in the process the red word. And then what? Then go back to the while, test is the file at the end, and read the next word. Now, think in terms of a hard disk, please. A hard disk is concentric metallic disks which can be magnetized and demagnetized. So it's something like this. We had seen this in the first part of 111 course. A read-write head moves inside and outside, right, to an angle, positions it on a track, and then looks down, waits for the data to appear under it, and then picks it up, reads it, so simple. Now, let's assume your whole text file, 100 megabytes, sits in adjacent something like this. Right? Now, you read something, what is going on actually down there? The file system knows on which part, on which sector, and which track your information lives. Let's say it lives over here. Pulls the head to that track and starts waiting. Remember, there was a time gap. We call that latency. Because we don't know where the rotating disk is exactly at that moment. Let's say it was over here. So we wait until it turns and comes, exactly below the reading head. And then the reading head reads it. The disk continue to spin about 120 times per second, right? So the moment it is read, it is gone. And then you process, presumably something very simple to do. The process, you come back, you test for the file being at the end. No, it's not at the end. You give the order to read the next word. The disk has turned. The disk has turned to this process, and now it is here, and you have to wait till it appears back on here. Terrible. So you read word by word, but at every reading you wait, in the worst case, for one cycle or some fraction of the cycle, but it's not nice because 120 turns means about 10 milliseconds. That's true. 10 milliseconds is usually the access time, average access time of a disk. So what you do? Actually, the operating system does it for you already. It reads more than you ordered him. It reads the whole stuff, fills it in some place in the memory. Remember, memory access is much faster. Much faster compared to 10 milliseconds. It's 100 nanoseconds. In between there's microseconds, right? 1,000 times faster. So it stores more than you have ordered to it and keeps a book about it. Mr. Richard ordered me to read this part, but I have read the forthcoming million characters also and stored it into the memory. And now you come to this position. Scanf, give me the next word. I tell you as an operating system, yes sir, I go and pick it from the memory and deliver it to you. Just a couple of more bookkeeping, this is also given, etc., etc. How long can I do this until I am finished with the whole stuff that I have read in, right? The same would exist if I would be writing. If I would be writing, I tell you, have you written it? Yes, sir, I have done it. Actually, I write it somewhere in the memory, in an array. And when the array is full, I grab the hard disk on, and with one shot, I dump all the huge array of, let's say, a couple of million elements. Unless the bucket or the memory is full, I store everything in the memory. Clever, provided that there is no electricity cut. When it is full, I go and dump it to the disk. This is called buffering. Buffering. Let me write it for you. Buffering. You don't go to the actual device every single instance. You go once, grab it as a whole, and then put it somewhere in the memory, because memory is not so short in these days. And then you give it from the memory. Quite intelligent, as I said, provided that there is no electricity cut. Okay, but is this always convenient? And what mechanisms do we have? Actually, whenever you open an F open, the file system manager and C both agree on an intermediate place in the memory. A couple of 100 bytes, not much. I was talking about millions of bytes. No, so just a couple of hundreds still is quite okay. And attach this buffer to the internal structure of the file system, and this file system reading mechanism, the file manager, which is in close communication with fopen and any F operations, fills that buffer first, a couple of hundreds, and then consumes from there. You had some experience with C programming. You might have experienced already the effect of this buffering. Sometimes, especially in the early days of C programming, you write a program and the program crashes. You make a terrible mistake, especially when you are playing around with arrays and pointers. You get your hands on a place in the memory which doesn't belong to you, and you are kicked out of the memory. You're kicked out of the memory. Now, you try to localize where is it happening. Of course, a way is to go and use the debuggers, but people like me, many of my friends and people in the department use printf debugging. Printf debugging is injecting printf statements at suspicious point in your program, so you discover where the breakdown of the program happened. Right? But there is another problem. You printf something and the crash happens and nothing appears on the screen. This way or that way, you make sure that actually that printf should have printed something on the screen, but it didn't. And you know that it has passed that point. How can this happen? How can a printf not appear on the screen? Because printf has also a buffer attached. Your standard output stream, now it's time to talk about that one as well. Your printf goes to a pre-assigned stream, very much like fopen, right? It goes to std out stream by a printf printf operation, and it got stuck in there, and then your crash happened, and that printf entity was printed in a place in the memory, in a buffer. It sits over there, and then your program crashes, and nobody takes that buffer and puts it on the screen before the crash. So it vanishes somewhere in the memory. It doesn't get the chance to hit your screen. Till then, till a \n gets printed. \n, new line character in C, is something special for printf. It tells also the buffer to empty. So till you have a \n printed, everything goes to that a couple of hundred bytes buffer internal, not on the display. When you print this, it appears on the screen. Well, for your case, it's very simple. For debugging, then you have to put a \n at the end of your printf, and then, of course, prior to the crash, it has to appear on the screen. You solve your problem that way. Now, how many buffering methods do we have? Full buffering, line buffering, and funny but existing, more buffering. Scanf and printf, the moment you open up your C program, starts in a line buffering mode. No books tells about this, but your teacher tells about it like now. So line buffering is the default for printf. That means until you have \n being printed, everything goes to the intermediate buffer. Who allocates the buffer? At the start of your C program, there is an overhead which is invisible to you, talks to the operating system and opens three channels, 3 streams. Whether you like it or you don't, they are automatically opened. What are they? std in, std out, and std out. These 3 streams of file pointer type are automatically created by the initial part of a C program's running. std in is where you read from, std out is where you write to, and stdr is where you write your errors. So actually print f, which you have used up to this time, is nothing else but an f print. If you put anything in here, f print std in and std out, sorry. std out, std out, whatever you write in there. Actually, your printf is defined to be so. So you have your standard keyboard and screen already allocated by a pre-running part of your program. And std out, the secret hand that opens std out, opens it in a line buffering mode. Now, if you want to change this line buffering mode exists for all type of fopen file as well. You are silently typing in fopen something, as I did in the previous blackboard. Silently it is opened with a line buffer of a couple of hundreds bytes. This is always done in this manner. Now, if you want to change this, then you have the right to use sorry, I'll clean up the board first. There is a function, set vbuff, which takes a file pointer in, like my input, and then a char pointer this is the string handle. This is the buffer head pointer. Then integers which has the buffer type or kind, and then the long int that tells the size of the buffer. Size of the buffer. So, you first fopen the file, and right away after that, you call this function. This unties the allocated a couple of hundred bytes, automatic allocation. Instead of that, ties the file to this buffer that you have provided. From here you provide the file handle, trivial. From here you provide an array of bytes, the pointer to the first element of an array of bytes. How big is this array depends on you. You put also the length in here. So if you had, let's say, 10 million of bytes array, you put in here 10 millions. How do I do the allocation? Two ways. Either you do it statically, like char, woof, millions. Can I do this? Yes, sir, you can do it. And then feed in here the buff. Or you do it dynamically at runtime by a malloc. Malloc and 10 million. Can I do this? Certainly you can. Certainly you can. Of course, you better check whether malloc succeeded, because maybe you are not allowed to take that many big an array dynamically. That's some other problem. Of course, always after a malloc, you shall check whether you received a null pointer which tells you I couldn't do it, or something else. Then take it and plug it in here. Here it is still 10 millions. And here the buffer type is one of these. For that purpose, we have define macros. Right? Define macros. Strange entities, but they come from stdioh defined. You cannot change them. Underscore io fbf underscore io lebf underscore io no nebf. Do you have to memorize these? Unfortunately, yes. You shall know it by heart. So in here goes one of these. One of these goes in here. This tells which way you want to have a buffer. Of course, it would be the most silly way to allocate 100 million bytes and then tell the system, I don't want to have a buffer. Of course, we don't do that. In that case, nobody checks it for. You can make such a funny mistake, waste your memory. But when you say null buffering, from here usually we send from here a 0 and from here null. That is the proper way to use it. But there is nothing wrong except the logic if you send from here a buffer that is not 0 length. But you shall not do it, of course. From that moment on, if you don't want to corrupt your system, you shall not play with the allocated memory. You allocated, I know. You can look into it. Yes, you can. Shall we? No. Systems storing their various formats of information, you don't have the right to interfere with that. Okay, now you may wonder what the details of these are. Full buffering means I provide you a buffer until the buffer is full. If we are writing, until the buffer is fully used, don't proceed with writing to the actual device. And if it is a reading device, if it's a data source, then with the single action of reading, read all this 10 millions of bytes in there, fill out the buffer, and whenever the guy asks for a single entity from the file, if it is present in the 10 millions, just as an example, the 10 millions, provide it from here. Can we change the buffer? Certainly, here you cannot. On the buffer, you cannot, you shall not, terrible mistake, etc. Can we do it by other ways? Yes. For that purpose, we have something that we call random accessibility. We randomly access the place we want to change, and we change it, provided that we do a special operation that will be explained later. But on the buffer, we do not do anything. It is served, submitted to the operating system, and the operating system does the reading for us. Okay, line buffering is something what I explained already. Until a \n character appears, everything which is printed goes to the buffer. If this is a reading device, if it's a data source, then until a \n or the end of file is hit, everything is read into the buffer. And then provided from there to you. Any scanf will silently go and pick from that internal buffer and provide it to you much faster. And we come to the no buffering phase. Why shall I do no buffering? Well, let's assume you are writing a missile control program. It tracks the target, and when the displays it somewhere, and then when the gunman pushes the red button, it fires it. Okay. In the implementation part, the missile, as I just in the previous lecture explained, is just a device. You open the device by fopen. Something so clean and not complicated and innocent. You just fopen a missile device. And then, let's say, the guy pressed the button, you sense it, you send to the device the special code to fire it. Let's say it is 1. You print to the device a 1. Nothing happens. Nothing happens because your print character goes into a line buffer. Why? Because any file, your special device, your missile device, when F opened, has a silent line buffer attached to it automatically. This is so for all files. So the system tells you actually fire a couple of hundred missiles more than I send them all together. Of course, this is something that you cannot stand. For a missile, we don't want to have any buffering at all. Even if F opens assigns automatically a small buffer, that small buffer would kill me. Therefore, after the opening of the missile device, for example, I set VBuff, the missile device, buffer null, buffer type, no buffering, underscore IO, no buffering in here, and the buffer size 0. Then any single byte will go directly to that device. No buffering will happen. This is also so for anything that you read in and want to process. When you want to have a direct input from the device, you set it to no buffer. Okay, here we stop, and in the next following lecture we continue with the random accessibility subject.